Okay, great. Thank you. Thank you. Thanks very much for the invitation. So, so I want to report on joint work with Peter Quirks. So we have a couple of papers in preparation that are coming up soon, actually 3 papers. And I would just want to give the main ideas in this work. So let me begin actually by recalling an old set of results from Constant from 1963. Which turns out to play a key role in our work. So Constant said that for a complex semi-simple group, G, with its Lie algebra 5G, first of all, there's a global slice for the coadjoint action on the set of regular points in the dual of the Lie algebra. So the regular locus here is those points for which the coadjoint orbit is of maximal dimension. Okay. So there's a global slice, meaning it's a smooth subvariety which intersects every coadjoint orbit transversely and exactly once. So I could have stated this result for the Lie algebra instead of the dual because they are isomorphic, but we'll soon generalize that to other Lie groups and Lie algebras which don't have this property, so that's why I'm stating it in that way. The second result is that all these, for all points in the regular locus, the stabilizers are abelian. So it's easy to see that the Lie algebra is abelian, but it requires a bit more work to show that the Lie group is abelian, even if it's not connected. And the third result is that this set of regular points, which is open and dense in the dual of the Lie algebra, satisfy the property of being a Hartog's open set, meaning that every holomorphic functions on that open set extend to the whole thing. Actually, the result is that the complement is of codimension 3, which is greater than 2, so Hartog's theorem holds. The only property we're using is that it's Hartog's. Okay. So the upshot of the talk where we're aiming for is to explain that for any Lie algebra, not necessarily semi-simple, that satisfy these 3 properties, or more generally, you can replace the dual of a Lie algebra by an affine Poisson variety, so a complex affine variety with a Poisson structure, satisfying analogs of that, stated with the notion of symplectic groupoids. Then this defines some kind of topological quantum field theory valued in Hamiltonian spaces. So what does that mean? I will say that in more precise details, but basically this is a way to associate to every, was there a question? Every surface with boundaries, a Hamiltonian space, so a manifold with an action of a Lie group and a moment map, in such a way that gluing surfaces correspond to Hamiltonian reduction on the other side. So again, I will state that in more precise terms. The case where this Lie algebra is a complex semi-simple Lie algebra, and so we have Constant's theorem, then this solves part of the so-called Moore-Tachikawa conjecture, which I will explain in the next slide. And the main novelty in our work is to explain why this, to prove this, using the notion of using shifted symplectic geometry and a certain notion of the one-shifted Weinstein symplectic category. So you know this Weinstein symplectic category is the category whose objects are symplectic manifolds and whose morphisms are Lagrangian correspondences between them, which generalizes symplectomorphisms when you take the graph, but it's more general. And we have a one-shifted version of that, which is kind of the intermediate step that explains this association. Okay, I will explain that. So first of all, let me explain what is this Moore-Tachikawa conjecture. So the basic ingredient is a complex semi-simple group, and S is the slice in the slide before. So this is the global slice for the coadjoint action on regular points. Okay. So there are 3 Hamiltonian spaces that we can immediately associate to that data. The first one just depends on the group G. So as you know, if you take the cotangent bundle of a group, of a Lie group, this is a symplectic manifold. The canonical symplectic form gives the symplectic structure. And it has 2 actions by G, by left and right translations, which are Hamiltonian. So there's a moment map. So this is the first one. The second one is a symplectic subvariety of that. So we're taking G cross S, where S is the global slice, viewed as a submanifold, and it's a symplectic submanifold. We've broken some of the symmetries, but there's still the left G action which continues to act on that. And so that's still a Hamiltonian space for one of the G actions. Then you can go one step further and take the set of pairs G, Xi, where Xi is in the global slice, where G stabilizes C. And this is, again, a symplectic submanifold of the second one. But we've broken all the symmetries, but we think of it as a Hamiltonian space for the trivial group action. Okay. So the goal of the Moore-Tachikawa conjecture is to extend that list of Hamiltonian spaces by having spaces with 3 G actions, 4, and so on. In fact, we want to think of them as being, these 3 as being associated with the cylinder, the cap, and the sphere in some way. So why am I associating them in this way? So I'll call them M cylinder, M cap, and M sphere. Because they behave a bit like gluing of surfaces when you take Hamiltonian reduction. So for example, if you take 2 caps together, you glue them, you get a sphere. And correspondingly, if you take the Hamiltonian space associated with the cap and take, so you take 2 of them, you take 2 of them here. This has, both of them have a G action, so you can consider the diagonal G action on them and take symplectic reduction. That's an operation that you can do. This gives you a new symplectic manifold, and it turns out to be the one associated with the sphere, so the third one here. And similarly, if you take a cap and a cylinder, and glue the cylinder on the cap, it's homeomorphic to the cap still, like a disk. And the same hole, so if you take the Hamiltonian space associated with the cylinder and the cap, the cylinder has 2 actions, you just pick one of them, and you take the diagonal action and do symplectic reduction. You get the same as the one associated with the cap. So the conjecture says that you can extend that to associate to every surface with boundaries a Hamiltonian space, which has as many G actions as their boundary components, and such that gluing surfaces correspond to Hamiltonian reduction. So another way of saying that is that this extends to a functor from the category of 2-dimensional cobordisms to a certain category of Hamiltonian spaces. So 2-dimensional cobordisms here is just the category whose objects are union of circles, 1-dimensional compact manifolds. Morphisms are surfaces bounding them, and then you compose by gluing. And then on the other side, that's a new category. It's a category not defined in terms of its objects, but in terms of its morphisms. The objects here are complex semi-simple groups, and the morphisms is the morphisms that are Hamiltonian space. So a morphism from G to H is a Hamiltonian G cross H space. And then what is composition, what is Hamiltonian reduction? Here you have a G cross H space and an H cross I space. So both M and N have an action of H. And so you can take the cross product and reduce by the diagonal action. That gives you a space which is Hamiltonian G cross I space. Questions?
You must have said that, but is M supposed to be holomorphic?
Yes, everything is holomorphic. Yeah, actually, yes. So everything will be, I'll say more about that, but everything is a complex affine variety. So there's a technicality here that they might be singular, okay? This will, I'll explain that in a moment. So, but you can think of them as smooth holomorphic manifolds just as a first approximation. Okay, so. Yes, so it's a reduction at level 0, and it's in the sense of geometric invariant theory, so still an affine symplectic variety. But I mean, I don't want to go too much into the details. You can think as a first approximation as just symplectic reduction.
I guess what you have to do is tell me what says in the paper.
Exactly, so that was the next slide. Okay, it suffices to construct what we associate to the pair of pens. But of course, it can't be anything. It has to satisfy some relations. One of them is that if you glue a cap to a pair of pens, it's homeomorphic to the cylinder, so that corresponds to an identity for Hamiltonian spaces. And so Moore and Tachikawa, I should have said, those are physicists, and they came up with that conjecture by studying some supersymmetric quantum field theory, and they had not only conjectured this, but they had examples. And this is the reason why this was very interesting, because of the examples which were a bit surprising. Well, the first one is quite simple. If you take G is equal to SL2, this is supposed to have 3 actions of SL2, and you take threefold tensor product of the standard representation will with these three actions. Okay. And then for SL3, turns out to be the closure of the minimal nilpotent orbit in the exceptional Lie algebra E6. And then they didn't know any other examples. So that was the surprise. That was why people started to be interested, like what does the exceptional Lie algebra E6 has to do with SL3, and what's the pattern here? How can we extend this list? But since then, we have a couple of partial solutions, notably Braverman, Finkelberg, and Nakajima proved this for the case where G is SLN using the theory of Coulomb branches. It doesn't give you as explicit as this description of the first two, but it shows that there are still affine symplectic varieties. Then there's another construction by Ginsberg and Kashdan, which is a bit more ad hoc, but they construct these as schemes. So as I said, these are affine varieties. They should be affine varieties, but it turns out it's easier to describe them as schemes. So it's just the spec of an algebra. And if you can show that this algebra is finitely generated, then you prove the full conjecture. So it reduces the problem to some problem in algebra. And then also there's a version by Bielawski where you don't look at all Hamiltonian spaces, but just a like you look at a category whose morphisms are not necessarily Hamiltonian variety, but one whose moment map takes value only in the regular part of the Lie algebra. Then you can, but basically what you get is the smooth locus of the varieties that the Moore-Tachikawa conjecture are supposed to give, just an open dense subset of them. Okay. So to explain this, well, I will we'll recover actually the scheme version in the Bielawski's version using this shifted symplectic framework. So I want to explain this next, just give a brief introduction to that. So first of all, I have to talk about stacks. So we had already an introduction this morning by Shamar on differentiable stacks, but I just want to review that again. There's no harm in reviewing the same thing twice in different ways. So it's a generalization of manifolds, which is especially good for working with singular quotients. And basically, so let me illustrate the basic idea with a special case, that of a stack associated with a group action on a manifold. So to illustrate that, let's think about the set of all pairs consisting of a manifold and a Lie group action on it. Okay. So a question is, what would be a natural equivalence relation on this set, such that two pairs of a manifold and a Lie group action, if they are equivalent, then they have, for example, the same quotient, homeomorphic orbit space, or also some the same equivalent data, such as equivalent cohomology and so on. They represent the same orbit space and the same also equivalent data, but represented by different manifolds and Lie group actions. So of course, one trivial thing you can do is say, well, the Lie groups are isomorphic and you have an equivalent diffeomorphism between them. But that's much too strong than necessary. For example, if you have a free and proper action, you would expect this to be equivalent to the quotient with the trivial action. They have the same quotient, they have the same equivalent cohomology, and so on. So if you can define such a natural equivalence relation, then the stack of the group action will be the equivalence class. So this will be the more fundamental object, which will represent the quotient, but there are many ways to represent the same quotient, and you don't have to describe the quotient as something singular, like as a stratified space or something like that. It's just the equivalence class of this quotient. This is the more fundamental object. It turns out that to answer this question, it's much more natural to do it a bit more generally with Lie groupoids instead of actions of Lie groups on manifolds. So a Lie groupoid is a generalization of a group where the multiplication is defined only if the target of one arrow corresponds to the source of the other one. We can think of them as space of arrows. And for stacks, it's particularly useful to think of them as generalization of equivalence relations. So a Lie groupoid on M, you can think of it as an equivalence relation on M, but where there are more than one ways to identify 2 points, and you want to keep track of all the possible ways. So you think of them as arrows, where when you have an arrow, this is a way to identify points. And you want to understand the structure of how these arrows interact with each other. So the transitivity law of an equivalence relation corresponds to groupoid multiplication and so on. Okay. So what's the natural setup where you have more than one ways to identify 2 points? Well, for example, if you have a Lie group action on the manifold, where the action is not necessarily free, then 2 points in the same orbit have many ways. There can be many group elements mapping one point to the other. And so that's the main example of a groupoid. Is the action groupoid of G on M for G and action on the manifold M, where you think of the arrows as pairs G, X, where it points, the tip of the arrow is X and it points to G dot X direction. Okay. So then in that setup, we include these action of a group, Lie group on the manifold. And then the equivalence relation that we're after has a very simple interpretation. So 2 Lie groupoids are Morita equivalent. That's the notion of equivalence. If there's a third Lie groupoid with maps to both G1 and G2, such that H is some kind of pullback of G1, but also of G2. So it's diffeomorphic, isomorphic to a pullback of G1 and G2 for some appropriate notion of pullback of Lie groupoids. Okay. And then the stack associated to a Lie groupoid will be its Morita equivalence class. Okay. For example, a Lie group action would be one. And so to summarize, instead of describing singular quotients, we replace them by equivalence classes of manifolds with Lie group actions, or more generally, Lie groupoids. Okay. So now we want not just describe singular quotients, but we want to do geometry on them. So how can we do that? Well, first of all, we have to discuss about the tangent bundle. Okay, so if Lie groupoids, if stacks generalize manifolds, what is the tangent bundle of a stack? Well, the tangent bundle of a stack turns out to be the Lie algebroid of the groupoid. So just as Lie groups have Lie algebras, Lie groupoids have Lie algebroids, which are vector bundles over M, the base, together with vector bundle homomorphism to the M. But the stack is only determined up to Morita equivalence by the groupoid. And so this Lie algebroid, this tangent bundle is not just a Lie algebroid, but up to some equivalence relation, which turns out to be quasi-isomorphism when you think of this just as a two-term complex. So we just have one homomorphism, but you can think of it as a complex with just 2 terms. And you get quasi-isomorphisms if you change the representation of the stack with another Lie groupoid. Okay, so now that we have tangent bundle, what is a symplectic form? Well, it's useful to think of a symplectic form on a manifold as an isomorphism from the tangent to the cotangent. It's a special kind of isomorphism coming from a 2 form, which is closed. But just to keep it simple, let's just focus on that aspect. It's an isomorphism from Tn to T star n. So now what's a symplectic form on a stack? Well, it should be an isomorphism from the tangent complex to its cotangent complex, but it's only determined up to quasi-isomorphism, so it should be a quasi-isomorphism on these 2. But now there's an interesting question, like, how should we align these things? These are 2-term complexes, and there are essentially 3 meaningful ways of aligning these 2-term complexes to get a quasi-isomorphism. And so the question is, which one is the right one? There are 3 ways to do it, and it turns out that's the nice thing about shifted symplectic geometry is that all 3 ways are valid ways of defining a symplectic structure on a differentiable stack. And you get 2 new ones that just don't exist on a manifold. These are new structures which exist just when you have a non-trivial stack. The first way is zero-shifted, which recovers symplectic geometry when the stack is just a manifold. So just think of it as a trivial groupoid M going to M. But you have also 1-shifted and 2-shifted. And if you have higher stacks, you can have n-shift for arbitrary integer n. Okay, so we'll mainly focus on 1-shifted symplectic here, which can be described more explicitly in the following way. So I said it's a quasi-isomorphism, just like for a symplectic manifold, it has to come from some kind of form. Here it's a series of forms. For 1-shifted symplectic stack, we have a 2 form on the space of arrows, a 3 form on the space of the space of objects, satisfying a compatibility condition, which is the analog of requiring that the symplectic form is closed. So this is the generalization. And the other one is the non-degeneracy condition, that you get a quasi-isomorphism from the tangent bundle, which is a complex here, to the cotangent bundle. Okay. So the nice thing is that this recovers exactly the notion of quasi-symplectic groupoids, which was introduced almost a decade earlier by Bernstein, Koenig, Weinstein, and Zhu and Chu in 2004, which includes the theory of symplectic groupoids, which are integration of Poisson manifold. I'll come back to this, but just like a Lie algebra integrates to a Lie group, a Poisson manifold integrates to something which is a symplectic groupoid, so a groupoid with a symplectic form, which is a special case of these one-shifted symplectic stacks. And quasi-symplectic groupoids are integration of Dirac manifolds, okay, which is still a bit more general. The main example is if you take a Lie group G and take its cotangent bundle, so we already saw that this is a Hamiltonian G cross G space. It has two moment maps, and to the dual of the Lie algebra, this gives it the structure of a groupoid, and taking the canonical symplectic form in the 0,3 form on the base gives this the structure of a one-shifted symplectic stack. So this is one of the main examples. And then there's also a notion of one-shifted Lagrangians. So there's a notion of Lagrangians in any n-shifted symplectic stack, in particular one-shifted. So this is just a Lie groupoid morphism where you have a 2 form on the base of L, satisfying, again, a compatibility in a non-degeneracy condition. An example is if you take a Hamiltonian G space, or a smooth manifold with an action of, by the way, everything that I'm saying, the first part when I was explaining the Moore-Tachikawa conjecture, I had to restrict to complex varieties. Now in this shifted symplectic setup, I'm describing them just in differential geometry. So everything is just smooth manifolds. And then we can specialize that to complex algebraic varieties later on. But so far, this is just smooth manifolds. So here, this is just a smooth manifold with an Hamiltonian action of a Lie group G. And it turns out to be an example of a one Lagrangian. On the base, you take the moment map. And then on the top, while you have G can be mapped to the G factor of the cotangent bundle, and you use the moment map also for the M factor. This gives us a homomorphism of Lie groupoids. And actually, if you have such a diagram, so just an action, and then you want to produce a one-shifted Lagrangian structure on that, this is equivalent to giving this the structure of Hamiltonian G space. So you conclude that Hamiltonian spaces are one-shifted Lagrangians. So keeping with the theme that everything is a Lagrangian, even Hamiltonian spaces are Lagrangians, but in the one-shifted setup. Okay, and this can be generalized further. So we have this theorem in the original paper on shifted symplectic geometry by Pantev, Toenvaki, and Vesossi, that if you have an n-shifted symplectic stack and two Lagrangians, then taking the fiber product, this will be n-1 shifted symplectic. And as a special case, if you take one shifted symplectic, so as we had in the previous slide, and Lagrangian, you get something zero shifted symplectic, which is ordinary symplectic geometry. So this can be used as a way to construct new symplectic manifolds from old, and in particular, symplectic reduction can be obtained in that way. So if you have a Hamiltonian G space, we saw one example of Lagrangian on the left-hand side. Just take the action groupoid. And on the right-hand side, you can take the group G itself viewed as a Lie groupoid over a point, embedded as the fiber over the neutral element. That's another one Lagrangian. And then the intersection is the action of the group G on the zero-level set of the moment map, viewed as a stack, just as I was introducing stack as equivalence classes of Lie group actions on manifolds. So this is an example. But if the action is free and proper, then this one is equivalent to the quotient. And so the quotient is symplectic manifolds. So symplectic reduction is a one-shifted Lagrangian intersection. It's a special case. More generally, you can talk about shifted Lagrangian correspondences. By that, I just mean a Lagrangian just like a Lagrangian correspondence in ordinary symplectic geometry, is the Lagrangian in the product of symplectic manifolds where one has the opposite symplectic structure. And so if you have two Lagrangian correspondences in this one-shifted symplectic sense, then you can take the fiber product and you still get a one-shifted Lagrangian correspondence from G1 to G3. Okay, so from that you can construct some kind of one-shifted version of Weinstein symplectic category where the objects are now one-shifted symplectic stacks and the morphisms are one-shifted Lagrangian correspondences. So there's still the issue, it's category in quotation as in the original Weinstein symplectic category because you have to require that the intersection is transverse in order so that we get a meaningful one-shifted Lagrangian. So not all compositions are well defined, but you can still complete this to a category in many different ways. So you can do the derived fiber product, either in the algebraic geometry sense, or perhaps in the sense that Shamar explained to us this morning. But you can also do the so-called Woodward trick, which is just to, if you can't compose two Lagrangian correspondence, you just keep them as a sequence of two Lagrangian correspondences, or a sequence of many Lagrangian correspondences up to an equivalence relation when if you can compose them, then you do. So it's just like a formal trick to extend this to a category. Okay, so let me go back to the Moore-Tachikawa conjecture. So this conjecture was to get some kind of functors where the target category is the category of Hamiltonian spaces. And just as we saw that Hamiltonian spaces, Hamiltonian reduction can be viewed as a Lagrangian intersection, one-shifted Lagrangian intersection, this composition here, which is a Hamiltonian reduction, but keeping in track some residual actions of G and I, can be viewed as a Lagrangian intersection of one-shifted Lagrangian correspondences. So composition in the category of Hamiltonian spaces is nothing else than intersection of one-shifted Lagrangian correspondences. Okay, so this idea was first observed by Kalak, and he proposed that maybe that would be a good formalism to prove the Moore-Tachikawa conjecture. And basically replacing the category of Hamiltonian spaces by this category of one-shifted Weinstein symplectic category. And our main contribution is to show that indeed that was a good idea. We're constructing these TQFTs valued in the one-shifted Weinstein symplectic category, and then we're showing how to get back to the Hamiltonian spaces with a little bit of caveat is that you have to take this. This is the first part is completely differential geometric. When you have to go to the algebraic world, you have to take some kind of algebra geometric quotient, and it gives maybe schemes rather than varieties, and then you have to work a little bit more to show that you get varieties. Okay, so how do we get these functors from two-dimensional cobordisms to one-shifted Weinstein symplectic category? So that's the next step. It's very useful to view these two-dimensional topological quantum field theories. So these functors are called two-dimensional topological quantum field theories, but it just means that it's a functor which respects the symmetric monoidal structure on both sides. So cobordism category has a monoidal structure where if you have a bunch of circles, you can take their unions, and then this is the monoidal structure, just unions of surfaces, unions of circles, of one-dimensional compact manifolds. And then a TQFT is a functor from that to another symmetric monoidal category. Usually, like the original TQFTs were in the category of vector spaces, C were vector spaces, where the monoidal structure is just tensor product of vector spaces. But this nowadays has more general, this is studied in more generality where you replace this by other categories, such as the category of Hamiltonian spaces that I just described, and the one-shifted Weinstein symplectic category. So the basic idea is this category of two-dimensional cobordisms is generated by on objects by circles, okay, by just one circle. An object is a bunch of circles, so just with one you can generate all of them by unions. And on morphisms by a list of 6 generators up to relations. So every surface can be chopped into pieces consisting of these 6 objects, and every relation possible on surfaces with boundaries can be obtained by this list of this finite list of relations. And so to construct a TQFT, it suffices to associate to each of these 6 generators a morphism and check that the corresponding relations hold on the target category. Well, first of all, you have to specify an object, which will be the object mapped by the circle. So the circle will be mapped to one object, and then 2 circles, since it's a monoidal functor, will be mapped to X tensor X. Tensor here can be any monoidal structure. In our case, it's just the Cartesian product of Hamiltonian spaces. And then, well, we have 6 morphisms, but 2 of them are already given. The cylinder here is the identity, so this has to be mapped to the identity. And the twist here, this is the symmetric structure on our category, so this also has to be mapped to the symmetric structure. So this is just swapping the 2 factors in the tensor product. And so there only remains 4 morphisms to specify, which are called unit, product, co-product, and co-unit. Why all them? Let's say the pair of pens, you can think of, this is a morphism from 2 circles to 1 circle. And so you can think of its association as some kind of product because it has to be a morphism from X tensor X to X. So it looks like some kind of product. And then the unit also is a morphism from the identity to X and so on. So we have to specify these morphisms, and it has to satisfy analogs of these relations. And once you have that, you call that a commutative Frobenius object in the category. And any commutative Frobenius object in the symmetric monoidal category gives rise to a functor, symmetric monoidal functor, which we call a 2-dimensional topological quantum field. Okay. So we want to construct commutative Frobenius objects in the one-shifted Weinstein symplectic category. How do we do that? Well, the first thing we can do is take an abelian Lie-Gupoid, and in this case, it's almost too easy. It's already given to us in the following sense. So if you take an abelian Lie-Gupoid, what I mean by that is that the source and target maps are equal, and all fibers are just abelian groups. Okay, so it's just like a family of abelian groups parametrized by a base n. Groups don't have to be isomorphic. It's not a bundle, but it's just a family of abelian groups. Together with a one-shifted symplectic structure, so that's the structure of a quasi-symplectic groupoid, this is a commutative Frobenius object in the one-shifted Weinstein symplectic category. And as I said, the structure is already given to us. The product is basically groupoid multiplication. It has to be a Lagrangian correspondence from A cross A to A. And you just take the set of composable pairs, and then you include that in A cross A, and you take the product to get something in A. So it's just the product of the groupoid multiplication, give us the product. And the unit is, not so surprisingly, the identity section of the groupoid. And so the unit should be a map from a point, a Lagrangian correspondence from the point to A, and it's just n viewed as a trivial groupoid over itself, included as the identity section. And then co-product and co-unit are the same, just swap these diagrams. And as a corollary, we get that every quasi-symplectic groupoid, more eta equivalent to an abelian one, doesn't have to be abelian itself, but it represents the same stack as an abelian groupoid. Then this will induce a TQFT because if they represent the same stack, anything on one stack can be transferred to anything on the representative of one stack of the stack can be transferred to another representative. And so in particular, these Lagrangian correspondences can be transferred from the abelian to the non-abelian quasi-symplectic groupoid. And so we get these one-shifted Weinstein symplectic, these TQFTs valued in one-shifted symplectic category from these abelianizable quasi-symplectic groupoids. Okay. Now, let me just restate this as a theorem. For every quasi-symplectic groupoid, that means one-shifted symplectic stack, equivalent to an abelian groupoid, so they represent the same stack, this induces a TQFT, so that's just a functor from cobordisms to this category. Now, how do we get examples, and how do we use that to tackle the Moore-Tachikawa conjecture? Now, at this point, I want to go back to these results of constant that I stated at the beginning. That will be important. So this says that we have a global slice for the set of regular elements in the dual of the Lie algebra, that the stabilizers are abelian. So you already see that the fact that these stabilizers are abelian might be relevant to us. And the third one, which will come later, is that this set of regular points is Hartogs. Okay. Oh, I stated it in that way. Hartogs mean that holomorphic functions extend, but also in particular algebraic functions extend. So this C bracket means algebraic functions. And so every algebraic function, every rational function on the set of regular points is actually just polynomial. It extends to the whole vector space. Okay, so 1 and 2 implies, first of all, that the cotangent model of the group, that was our first example of a one-shifted symplectic stack. So the cotangent model of a Lie group with its canonical symplectic structure is one-shifted symplectic. In particular, if you restrict it to the regular points, it's still one-shifted symplectic. And 1 and 2 imply that the restriction to the slice, first of all, is Morita equivalent to the restriction to the regular points, but also it's an abelian Lie groupoid. So the source and target maps coincide, and it's just a bundle of groups. This one is called the universal centralizer of the group. It's very well-studied space. And then immediately we get a regular version of the Moore-Tachikawa conjecture, which recovers results of Ginsburg, Kanzler, and Piolavsky. So this is the version where we only consider Hamiltonian spaces whose moment map take values in the regular part of the Lie algebra. But we are interested in getting the whole Moore-Tachikawa TQFT, and this is where the third part is useful. First of all, so I said that every the composition in the Hamiltonian category is a one-shifted Lagrangian intersection. Okay, so if you have in this category of Hamiltonian spaces, and then you do a symplectic reduction to do composition, this is an example of one-shifted Lagrangian intersection. Conversely, you can go back. In the differential case, if you have any one-shifted Lagrangian, so this is a one-shifted Lagrangian correspondence, G1 and G2 are one-shifted symplectic Lie groupoids, and this is a one-shifted Lagrangian correspondence. You can show that this is equivalent to a Hamiltonian space for G1 and G2 in the generalization of Hamiltonian spaces where it's not group that acts, but quasi-symplectic groupoids. And then you can show that this is equivalent to a Hamiltonian action of G1 and G2, not on a manifold, but on a stack, so on a Lie groupoid representing a stack. And so if you want to get a space, you have to kind of take the orbit space of that stack. But this is not always well defined. In general, you get some complicated stratified space. Or if you restrict yourself to algebraic geometry, you can do this quotient in the algebraic geometric sense. And so this is the quotient that we have here. Let's not bother too much about the details of what is inside here, but basically is making this equivalent to an action groupoid and then taking the quotient in the algebraic geometric sense, which means taking the global functions and taking the invariant parts of these functions and taking the variety associated to that, so the spec of this thing. And so this is a theorem that we get a functor. I mean, functor should perhaps be in quotation because it's only defined in some subset of the morphisms, but nevertheless, the composition after the first one with the cobordism category will be a genuine functor. Okay, so now this is where 3 is coming. So this composition can be defined. And in the first part, we only did this over an open dense subset, so it doesn't recover the whole thing. But it's not any open dense subset. It's sufficiently large that it knows about all functions on the larger set. And so once we do this second step, this kind of affinization process, it kind of automatically completes to the whole thing to what we want. So we recover the whole Moore-Tachikawa conjecture, the scheme version. What I mean is that this is an affine scheme. If you want to show that it's a variety, you have to show that this thing inside is a finitely generated ring, which is a question for algebraic geometry. I mean, for just algebra. But we're still getting this a genuine functor for cobordism to this category of Hamiltonian schemes. A good part of the work was also to just construct this category of Hamiltonian schemes rigorously for arbitrary quasi-symplectic groupoids. Okay. So now let me kind of summarize and generalize in the same slide. So let's say that we want to do this a bit more generally. We will replace the dual of a Lie algebra by a smooth complex affine variety with a Poisson structure. Okay, so it can be any smooth complex affine variety with a Poisson structure. And suppose that it integrates to an affine symplectic groupoid. Okay, so as I said, just like a Lie algebra integrates to a Lie group, there's this theory of integration of Poisson manifolds to Lie groupoids with a symplectic structure on it. And we're supposing that this integration exists. Okay, so not every Poisson manifold integrates, but most of them do. And also that the integration is also an affine symplectic groupoid. So this is the case for the dual of a complex semi-simple Lie algebra. And we're supposing also that the analogs of Kostan's 1963 results on complex semi-simple Lie algebras also hold. So there's a global slice for the set of regular points. So those are the points where the symplectic Lie is of maximal dimension. And the isotropy groups are abelian, isotropy groups of the Lie groupoid over regular points. And that this set of this regular locus is Hartogs. So holomorphic functions extend. Then, in this case, this determines a TQFT, so a functor, from two-dimensional cobordisms to Hamiltonian schemes. And also, you can view this as a TQFT valued in the one-shifted, one-string symplectic category. So as an example, you recover the Moore-Tachikawa conjecture if you take the dual of a complex semi-simple Lie algebra, which satisfies all these three properties by Kostan's theorem. And so one of the features of this proof is also that not only like we recover these Hamiltonian schemes, but also if you don't like schemes and you just want to work with smooth things, you can just keep this with the one-shifted, one-string symplectic category because those are just Lie groupoids, smooth Lie groupoids with smooth maps, differential forms on them. Everything is just ordinary differential geometry. Well, these are actually holomorphic. Everything is holomorphic, but it's still differential geometry. But if you want to go to recover the scheme, there's this process here, which is some kind of affinization where you take an algebraic geometric quotient. Everything is completely determined by these Lie groupoids. So you can think of them as kind of the more fundamental object from which you can get the non-trivial affine varieties in the Moore-Tachikawa conjecture from this affinization process. Okay, so now there are a couple of questions that are obvious from here. First of all, what are other examples other than duals of complex semi-simple Lie algebras? So other maybe Lie algebras or affine Poisson manifolds which satisfy these three properties. It turns out that the third property is not too bad to formulate, I mean, to find examples. We have many examples of Lie algebras where the regular locus is Hartogs, but the main obstruction is this 1 and 2. And in fact, I should say that 1 and 2 can be made even more generally. You can just require that the restriction of the Lie groupoid to this Hartogs open set is Morita equivalent to an abelian Lie groupoid. 1 and 2 are sufficient, but it can be more general. It's just that we haven't been able to find any example which is not coming from 1 and 2 from a global slice, but perhaps they exist. So that's one question. So what are examples? Well, one of them is this five-dimensional non-reductive Lie algebra. Is the semi-direct product of SL2 with its standard representation viewed as an abelian Lie algebra. So this is five-dimensional, this is non-reductive, so non-semi-simple. If you take the dual of its Lie algebra, it satisfies 1, 2, and 3. There's a global slice for regular points, and so on. And so this gives us a new TQFT, and so it's worth studying. And also, now we know that the set of examples is strictly larger than the complex semi-simple Lie algebra. So this brings the very interesting question, at least interesting for us. We're wondering, like, what is the set, the class of Lie algebras which satisfy these three properties? Can we find many examples, and what are the associated TQFTs? How do we study them? Also, we have non-affine but regular Poisson varieties that work, because if, like these affine, the fact that we're requiring these to be affine is just to get this step here, to get Hamiltonian schemes in the end. But if you want to keep this, you want to skip that, you can have non-affine but regular Poisson varieties. This will give us a functor with the first arrow here, and then you can still get. In this case, we have an example with the Grothendieck-Springer resolution, which is the Poisson manifold that we're considering, and then we get these quotients here. Instead of doing algebrogeometric quotient, we can take actual orbit spaces, which will be manifolds, and we can construct these as genuine Hamiltonian manifolds acted on by the integration of the Grothendieck-Springer resolution. And finally, also the obvious question is, when are these schemes that we get in the end actual varieties? When can we integrate, when can we show that their coordinate ring is finitely generated? We know this is true for SLN by the work of Braverman, Finkelberg, and Nakajima on Coulomb branches, but like for example, is the one coming from this five-dimensional non-reductive Lie algebra? Do we get varieties? That's a very good question. Okay, I will end my talk here. Thank you for your attention.